Okay, let's move on from the basic Brayton cycle, ideal or otherwise. The ideal Brayton cycle has reversible compressors and turbine. Let's move beyond this typical Brayton cycle and let's look at strategies for improving the output, net power, specific work, as well as efficiency for a gas turbine. Let's look at some strategies, some devices, some ways that we can increase net power and perhaps increase the efficiency of a gas turbine. It's good to get as close as we can to the Carnot cycle efficiency and boost up power or network as much as we can. So there are three strategies that we're going to look at today for improving the performance, efficiency and specific work, let's say, or power, net power, improve the performance of a Brayton cycle. The three strategies are implementation of intercooling, or what's called multi-stage compression. That's where you break the compression process up into multiple compression processes instead of a single compression process through one compressor. So we'll talk about that in a moment. There's also reheat, or multi-stage expansion. That's where you have multiple turbines. Instead of, you expand the working fluid through multiple turbines instead of a single turbine. And then we have regeneration, or if you like, heat recycling. There are ways that we can take some of the heat that would have been rejected and use it to preheat the compressed air before it goes into the combustor. So we can actually recycle some of the lost heat, or implement a regeneration or use a regenerator to recycle some of the lost heat that would have been lost to the environment, and therefore we can improve the efficiency of our Brayton cycle. So let's talk about all three strategies here. We'll have TS diagrams up here to show you how they work. So we have, first of all, intercooling or multi-stage compression. Now, the original Brayton cycle had a single stage compressor. So the original Brayton cycle had, so here's S and here's T. So we had a single stage of compression, then we had the heat addition, and then we had expansion. So 1 to 2 to 3 to 4. This is the reversible device. So this is Q combustor, and this is Q out, and this was our adiabatic compressor and our adiabatic turbine. So the original Brayton cycle, ideal Brayton cycle, for example, had a single compressor compressing the fluid up to from Pmin all the way up to Pmax. Okay? Single compressor. Now, what we're going to do here is we're going to try to reduce the amount of work required to compress the air or the gas. We're going to try to reduce the amount of work by breaking up the compression process into more than one. In this case, 2 compressors, and we're going to cool the gas down in between the compression processes. So instead of having a single compression process from state 1 all the way up to Pmax, instead we're going to compress the fluid partially to some intermediate pressure. So this dashed line represents some intermediate pressure, or pressure in between Pmin and Pmax. And then once we get up to the intermediate pressure through our low pressure compressor, so this compression process from P1 to P2 is the low pressure compression process. So once we get to P2, the intermediate pressure, we're now going to cool the gas down. We're going to extract heat from it by passing it through some sort of a heat exchanger. This heat exchanger is called an intercooler. So the air goes into a low pressure compressor. It gets pumped up to an intermediate pressure. Then we reject some of the heat. We cool the air down through an intercooler. And then we complete the compression process in the second or high pressure compressor. So once we cool the gas down to some low temperature, T3, then we complete the compression process all the way up to Pmax in the high pressure compressor. So we've split the compression process up into two compression processes with heat rejection or cooling or intercooling in between. This results in a reduced amount of work, specific work or power required to drive the compressors compared to a single compression process. So intercooling results in a reduction in compressor work, total compressor work. So W dot low pressure compressor plus W dot high pressure compressor is less than the work required or power required to do it all in one compressor. Okay? So less specific work, less power to accomplish the compression process if we split it up into a low pressure compression process with an intercooler in between, completed with a high pressure compression process. Two compressors, one heat exchanger called an intercooler in between. Now we can do the same thing on the turbine end as well. We can do what's called reheating or multi-stage expansion. So we can increase the amount of power produced by the turbine or the expansion process by replacing a single turbine with two or more turbines. So here we have the combustor, and the outlet state for the combustor is state 5. So instead of having a single expansion in one turbine, we expand it through a high pressure turbine, which brings the pressure, so 5 to 6 is expansion in a high pressure turbine. Notice that these are irreversible devices here. Then, once we get to the outlet of the high pressure turbine, we reheat. We inject more fuel, and we burn more fuel in a combustion chamber called a reheater. So we add more fuel, temperature goes up, entropy goes up because we're releasing heat, and then we expand the now hotter air through a low pressure turbine until we get down to the minimum pressure. So we got P min here, and we got P max here, and we have some intermediate pressure in between. So let's go over this one more time. Hot products of combustion, hot air, from the combustor into the low pressure turbine, high pressure turbine, our first turbine. Add heat in a heat exchanger called a reheater. Add fuel, burn it, add heat. Heat up the air, heat up the exhaust, the products of combustion. Then expand, finish the expansion process in a second turbine called the low pressure turbine, LPT. This produces more work, more specific work, and results in more power produced by the gas turbine. Let me show you, let's put these two together, and I'm going to show you exactly where the extra power is produced. So these two strategies combined together in a single device result in increase in power. Now let me take the original, so let's have the original P max and P min isobars in the cycle. So I have P min and I have P max in the cycle. Now originally, for our regular Brayton cycle, let's say it's reversible, let's say it's an ideal Brayton cycle. Originally, we have compression all the way up to state 2, then we have heat addition, and then we have expansion in the turbine and heat rejection. So state 1 is here, compression from 1 to 2 in the compressor, heat addition from the combustor, then we have expansion in the turbine, okay? And then we have heat rejection in the environment. So that's a typical ideal Brayton cycle. Let me split up the compression process and the expansion process. So we put an intermediate pressure isobar in this TS diagram. Let's put an intermediate isobar. And now I'm going to overlay here. I got some blue chalk. I'm going to implement intercooling and reheating, and we're going to see what the cycle looks like. So I'm going to compress it up to the intermediate pressure in the low pressure compressor. Then I'm going to reject heat. So this is Q intercooler. Going to reject heat. Now I'm going to compress all the way up to my Pmax isobar. Now I'm going to add heat up to my Tmax. Now I'm going to expand in my high pressure turbine. And I'm going to add heat in a reheater. So here is Q reheat. Then I'm going to expand the working fluid in my low pressure turbine. And then I'm going to finish the cycle by rejecting the heat Q out. Recall the area bound by the TDS curve is equal to the net heat, Q net, which is equal to the cycle work. It's actually Q cycle, which is equal to the cycle work. Okay, we developed this when we talked about cycles just a week ago. So the area bound by the TS curve through over a cycle is equal to the cycle work. W cycle, not WW cycle. Okay? Now let's compare the areas. The original cycle without intercooling and reheating just had this area right here. Okay? The new cycle with intercooling and reheating has not only this area, but it has these additional areas. So the entire area bound by the TS curve is greater when you implement reheat and intercooling. So W net for the old original cycle is less than W net for the cycle having reheat and intercooling. So if you want to increase the amount of power produced by your Brayton cycle, good idea to break up the compression and expansion into multiple compressors and multiple turbines with intercooling and reheating in between. Some of you here might recognize the term intercooling. Some of you might recognize the word intercool. Any idea where that word comes from? Where have you heard intercool before? Motorheads. Any motorheads here? Well, intercooling comes in when you have a turbocharger in your car. You have a gasoline or a diesel engine and you pre-compress the air before it even goes into the combustion chamber, and you do it with a turbine, okay, a turbocharger. Now, once the air gets compressed in the turbocharger, it gets cooled down by a heat exchanger placed in front of the radiator on your car, and that heat exchanger is called an intercooler. So if you've got a turbocharged car, whether it's a diesel or a gasoline, it may say somewhere either in the owner's manual or maybe even there might be an emblem or a label on the car itself that may say intercooling or turbocharged with intercooling. I know I have a vehicle that says on the inside of the car, on the control panel, it says turbo diesel intercooling. So to increase the amount of power and increase the efficiency of your diesel or auto cycle, your gasoline engine. Sometimes they implement intercooling between the turbocharger and the engine, okay, to increase power and increase efficiency. Okay, let's talk about regeneration. What is regeneration all about? Well, let's draw here a TS diagram for a Brayton cycle. Let's do it for an ideal Brayton cycle. Let's just do it for a plain old ideal Brayton cycle. We'll deal with the intercooling and regeneration with an example. So let's look at regeneration. So let's say we have a TS diagram here for our ideal Brayton cycle. Hold on a minute. I'm going to draw it a certain way. There we go. So compressor inlet, compressor outlet, heat addition from the combustor, turbine inlet, turbine outlet, okay? And then we have heat rejection going on here. Now I want you to notice something here with this particular cycle. Notice that the the turbine exit temperature, T4, this is T-turb exit. So let me draw the device here. Let's draw the device, make sure we're on the same page. So we have the compressor, we have the combustor where the heat is being added, and then we have the turbine. And the turbine's producing some work and the compressor's consuming some work, okay? The states, state 1, 2, 3, and 4. Okay. Now I want you to notice something here. The turbine exit temperature in this particular diagram is actually greater than the combustion inlet temperature. So T2 is T combustor inlet. There's a temperature gap here between the combustor inlet and the turbine exit. The turbine exit temperature is a lot hotter than the combustor inlet temperature. Now, heat naturally flows from hot to cold. So in theory, there should be some way that I can take the heat from the hot exhaust air, the exit of the turbine, I can take some of that heat and let it flow into the airflow before it goes into the combustor. I can preheat the combustor inlet gas. So I'm going to call this heat exchange Q regen, Q regenerate, Q regenerate, R-E-G-E-N, regenerate. Now what's a way I could do that? Well, instead of having this here, instead of having this over here, I can take the compressor outlet gases, air, I can feed it into a heat exchanger. Heat exchanger, or if you like, a regenerator. Regenerator. And I can take the exit turbine flow, which is hot. I could put them in thermal contact, so this will be a channel or a duct containing the very hot turbine exhaust. And this area or channel contains the relatively cool combustor inlet gases and naturally heat. Q regen will flow from the hot exhaust gases out of the turbine into the cool combustor inlet gases. So I could put a heat exchanger here installed between the combustor and the compressor, and I can attempt to get some of the heat that would have been rejected, that would have been wasted and rejected to the environment. I can attempt to pull some of that heat and use it to preheat the air before it gets into the combustor. Okay? Now the question is, what's the maximum amount of heat I could possibly get? Using this heat exchanger. So what's Q dot max? What's the maximum heat I can get using a regeneration process? Well, clearly the maximum amount of heat that I can pull, in theory, the very maximum amount of heat I can pull from the hot exhaust and shove it into the cool intake, the maximum amount of heat is the enthalpy associated with this temperature difference. So Q dot max regen is equal to m dot for the air times the enthalpy at state 4 minus the specific enthalpy at state 2. So this is the maximum possible enthalpy change. In theory, I could bring the compressor, the combustor inlet temperature and enthalpy all the way up to the temperature of the turbine exit, and therefore the turbine exit enthalpy. That's the maximum rise in enthalpy due to the regenerator. Okay? So this here is a max delta H. Max delta H. Now, in real life, we can't get the maximum. We can only get some fraction. So the ratio of the actual heat transfer, Q dot regen, to the maximum possible regenerator heat transfer is equal to what's called the effectiveness or efficiency. Okay? This is called the regenerator effectiveness or, if you like, efficiency. Usually a well-designed heat exchanger, a counterflow heat exchanger, maybe you can get an effectiveness of about 80%. Maybe. Okay, so the amount of regeneration that we get, compared to the maximum possible is typically around 80%. And that's defined, that ratio is defined as the regenerator efficiency or effectiveness. Now, if I have a regenerator here, I need some additional states. I need to redraw this TS diagram and reassign my states. Let's see, this is state 1. This is going to be state 2. This is going to be state 3. This is going to be state 4, 5. Then I have a 6, a 7, and finally I have an 8. So I have some additional states here. So I have some additional state. So 1 to 2, and then the regenerator outlet state is state 3. And now, instead of adding all that heat to from the combustor, all of it from state 2 all the way up to my old state 3, this is now state 4, this is my combustor outlet. Now I'm only adding heat from the regenerator outlet to the combustor outlet. So this is Q combustor. All this additional heat from 2 to 3 is now added in the regenerator within the cycle. It's recycled heat. I'm only having to add additional heat in the combustor from 3 to 4 now. The rest of it from 2 to 3 is recycled heat. Clearly, this is going to represent an increase in efficiency because I'm reducing the amount of heat I have to add in the combustor. Okay? Let's see, now I expand it down to state 5. I don't really need to worry about the rest of the states. Those are all having to do with the hot exhaust gas inside the regenerator. I don't really need that. So Q combustor with regeneration is less than Q combustor without regen. So that means that the efficiency is going to be higher if you add a regenerator. So eta with regeneration is going to be greater than eta, or efficiency for the cycle, without regeneration. So adding a regenerator boosts your efficiency, sometimes substantially. And by the way, doing multi-stage compression and expansion tends to improve the amount or increase the amount of heat you can add or recycle in a regenerator. Usually having multi-stage, I've only done this for single-stage compression and expansion, but adding multiple stages of compression expansion can result in an increase in the amount of heat you can recycle in a regenerator. Okay? So let's dwell on this for a minute. We'll do an example here. Okay, let's do an example here involving multiple stages of compression and expansion. So we have a Brayton cycle with two stages of compression and expansion. We'll talk about regeneration at the end here, but let's forget regeneration for the moment. We're going to look at a 2 compressor, 2 turbine with intercooling and reheat. Okay, so that's the plan for today. So let's go over the givens here. We have the low pressure, LPC, low pressure compressor inlet temperature of 300 degrees Kelvin. And then once the compression occurs, we go into an intercooler and we reject some heat. And then we go into a HPC, high pressure compressor, that's the second compressor, and we pressurize it all the way up to the maximum pressure. Now you're told here that each compressor and turbine has a pressure ratio of 3. So the ratio of the outlet to the inlet pressure for each turbine is 3. So 3 times 3 is 9, so I guess the overall pressure ratio from Pmin to Pmax is 9 times. The overall pressure ratio is 9. The turbines and compressors have 85% and 80% isentropic efficiency, respectively. The maximum temperature in the cycle, the combustor exit temperature T5, is 1200 degrees Kelvin. And the amount of intercooling and reheating is such that the high pressure compressor inlet, temperature T3, so state 3 is right here. the high pressure compressor inlet temperature is the same as the low pressure compressor inlet temperature. So these temperatures, T2 and T3 and T1 are the same. T3 and T1 are the same. We reject just enough heat in the intercooler to bring the high pressure compressor inlet temperature down to the inlet temperature for the low pressure compressor, okay? A lot of cooling is going on in the intercooler. Likewise, we are adding just enough heat in the reheater. So the reheating occurs between the high pressure turbine exit and the low pressure turbine inlet. We're adding just enough heat to bring the low pressure turbine inlet temperature back up to the maximum temperature, T5. So T7 is equal to T5. T7 is equal to T5. We're adding just enough heat. So T7 is equal to T5, and T3 is equal to T1. So we're specifying the amount of intercooling and reheating that has to occur in the cycle, okay? So needless to say, I guess I'm going to say it right here, pressure drops, delta P across the combustor, intercooler, IC, and reheater, RE, are 0. No pressure drops across the intercooler, the combustor, and the reheater. No pressure drops. Let's not worry about that complication. In real life, there's going to be pressure drops across any kind of heat exchanger. It may be large, it may be small, probably relatively small. So what are we supposed to find here? We're supposed to find the specific works of the high and low pressure compressors, the specific work of the high and low pressure turbines, the net specific work produced by the device, the heat input, how much heat is added to the device to make it work. And once I have the net work, the net specific work, the total heat added to the system, the cycle, I can calculate the efficiency, which is a ratio of the two. And then when we're all done with that, we're going to add on a regenerator here. We're going to stick a regenerator. We're going to stick a regenerator in here and see if we can improve the cycle efficiency, okay? The efficiency of the device. We'll talk about that in a minute, okay? All right, so let's see here. Let's get started here, analysis. Okay, so let's calculate the specific works for the turbines. That shouldn't be too difficult. We've done this sort of thing before. So specific work for the turbine, we want to get, first of all, we want to get WLPC, the low pressure turbine, okay? I'm sorry, compressor. W for the low pressure compressor. Well, we're going to run into the same problem we had last time on the last example we did. I don't know anything about state 2. I don't know what state 2 is, so I don't have a specific enthalpy at state 2. So when I apply the energy balance, I can't get the difference between H2 and H1, which would give me the specific work. So we're going to have to use the definition of isentropic efficiency to get WLPC. So notice the efficiency of the low pressure compressor is equal to the work produced, required for the isentropic compressor, and this would be low pressure compressor, divided by the actual work or power required by the, I guess I'm going to do Isen LPC. How about that? Isen LPC, divided by the actual power required by the low pressure compressor. Of course, I can write this in terms of specific. So W Isen LPC over W LPC. Because the mass flow rates are the same in the isentropic and the irreversible non-isentropic LPC. So W LPC is equal to the what? W for the isentropic LPC divided by the efficiency of the low pressure compressor. Okay? Now, if you apply the energy balance to the isentropic compressor, isentropic compression process, you'll get H2 sub S minus H1, again divided by eta LPC. Now, H1 is going to be H evaluated at T1, which is what? 300 degrees Kelvin? Let's see here. Yes, 300 degrees Kelvin. So it's going to be about 300 kilojoules per kilogram. kilojoules per kilogram. If we go through and note, process 1 to 2 sub S, we have PR2 sub S over PR1. It's an isentropic process. Isentropic. So we have PR2 sub S equal over PR1 is equal to P2 over P1. And that's equal to my pressure ratio for the compressor R sub P. R sub P. R sub P is equal to 3, I know that. Let's see here, PR1 is PR evaluated at T1, which is 300 degrees Kelvin. What's PR1? What's PR1 here? Let's see here, PR1. 1.386, 1.386, that's from tables. 1.386. Okay, so PR2 sub S is equal to R sub P times PR1. So that's 3 times 1.386. And I get a PR2 sub S. PR2 sub S is equal to 4.16. 4.16. So H2 sub S is H evaluated at PR equals 4.16. PR2 sub S, and I get an H2 sub S 411.26 or 411.3. 411.3 kilojoules per kilogram. Okay, so I have H1, I have H2 sub S, and I have the isentropic efficiency for the compressor. So I get 411.3 minus 300 kilojoules per kilogram divided by the isentropic efficiency for the low pressure compressor. The isentropic efficiencies for all the compressors and turbines is 80% and 85 respectively, so I need to put a 0.8 in there. 0.8, or if you like, let's see here, I should crank this out. Or if you like, WLPC is 411, forget the 0.3, minus 300 divided by 0.8. And I get 139 kilojoules per kilogram. A little bit of rounding going off on there. Okay, so let's write the first result down. WLPC is equal to 139 kilojoules per kilogram. So WLPC equals 139 kilojoules per kilogram. I got a number there, good. 139 kilojoules per kilogram. Okay, now let's figure out what WHPC is. What's WHPC? What's the high pressure compressor specific work? Well, before I go through and crank out a bunch of stuff, let's just have a look at the TS diagram. Notice that my inlet temperature and therefore inlet enthalpy for the high pressure compressor and the low pressure compressor are the same. That's stated in the problem statement. T1 is equal to T3. Therefore, H1 is equal to H3. Notice the pressure ratio is the same. The pressure ratio is the same for all compressors and turbines. The inlet enthalpy is the same. The pressure ratio is the same. The isentropic efficiency is the same. So H4 is going to be equal to H2. The specific work for the high pressure compressor is going to be the same as the low pressure compressor. Same pressure ratios, same inlet temperatures, same isentropic efficiencies. It's the same device. So right over here, I'm going to write, let's make this quick. WHPC is equal to WLPC. Why? Because the inlet temperature T1 is equal to T3. The pressure ratio RP is same. And the isentropic efficiency for the compressor is the same. So you go through the calculation, you'll get exactly the same outlet state and therefore the exact same specific work. So WLPC is equal to WHPC, and they're both 139 kilojoules per kilogram. So WLPC equals WHPC, 139 kilojoules per kilogram. Okay, it's both the same, both the same. All right, let's calculate the specific work for, so I'm going to put it here. WHPC is equal to 139 kilojoules per kilogram. Okay, same thing. Let's do the high pressure turbine. Let's do W high pressure turbine. Let's do that, W high pressure turbine. We're getting there. 2 out of the way. 2 out of the way out of 8 or something. We're getting there. So the high pressure turbine, expansion process on the high pressure turbine that occurs from state 5 to state 6. I know the temperature at T5. I don't know anything about state 6. I don't have a temperature. We're running into the same problem here. If I try to apply the energy balance from process 5 to 6, I don't know H6. So I think I better start off with the definition of isentropic efficiency for the high pressure turbine. The isentropic efficiency for the high pressure turbine is defined as the actual power output, W dot HPC, divided by the maximum, which is from the isentropic high pressure turbine. So W dot HPT, high pressure turbine, divided by the isentropic work, or the work produced by the high pressure turbine operating isentropically. Therefore, and of course this is equal to WHPT over W isen HPT. Why can I do this? Because the mass flow rates through the isentropic and the actual turbine are the same. Okay? So this implies WHPT equals the isentropic efficiency of the HPT times the specific work for the isentropic high pressure turbine, or the high pressure turbine operating isentropically. Now, if I apply the energy balance to the isentropic turbine, I get eta HPT times, let's look at our TS diagram here. So the isentropic process goes from 5 to 6 sub s instead of 5 to 6. The real turbine goes from 5 to 6. So 5 to 6 sub s. So this is H5 minus H6 sub s. Okay? Now I know H5 because I know the I know the combustor exit temperature. So H5 is equal to H evaluated at T5. What is that? 1200 degrees Kelvin? Let's have a look here. 1200 degrees Kelvin. I think it is. So the maximum temperature of the cycle, the combustor exit temperature, that is 1200 degrees, T max, 1200 degrees, looks good. And by the way, before we get too excited here, remember these turbines and compressors, each individually has a pressure ratio of 3. Just a reminder here, because we're going to use that in a moment. Okay, so I know H5. Let's see, let me get H5 here, evaluated at 1200 degrees. I get 1278 kilojoules per kilogram. Kilojoules per kilogram. 1278 kilojoules per kilogram. Okay, so I got H5. I need to get H6 sub s. Again, let's look at the process. 5 to 6 sub s, and this is an isentropic expansion process. So I can write PR5 over PR6 sub s is equal to P5 over P6 sub s, which is P6. Let's see here. P5 is the higher pressure. So P5 is greater than P6, and the pressure drop across the turbine is 3. We're told that in the problem statement. So this is RP again. Okay? So PR6 sub s. PR6 sub s is equal to PR5 divided by the pressure ratio, the turbine pressure ratio for the high pressure turbine. PR5, that is PR evaluated at 1200 degrees Kelvin, which is T5. And I get a PR5, 238. That's pretty high. 238. 238. That is PR at 1200 degrees. Okay? So we have PR5, 238 divided by the pressure ratio, which is 3, and I end up with PR6 sub S. Reduced pressure at 6S, 79. I get 79. 79. Now, H6 sub S is H evaluated at PR6 sub S, which is 79. And I looked that up in a table. And I get H6 sub S is 946. 946. 946 kilojoules per kilogram. Okay? So now I have H6 sub S, I have the isentropic efficiency. Whoa, okay. Let me plug in. What's the efficiency of my turbine? Let's have a look here. Isentropic efficiency of each and every turbine is 85%, so 0.85. 0.85. H5 is 1278 minus H6 sub S, 946 kilojoules per kilogram. And let's see what I get. So 1278 minus 946 divided times 0.85. 282 kilojoules per kilogram. So that's the specific work for the high pressure turbine. Let's write that in our results. 282. WHPT is 282 kilojoules per kilogram. WHPT equals 282 kilojoules per kilogram. Okay? All right, what about the low pressure turbine? Guess what? Same issue as for the high pressure compressor. We are told that the reheating increases the temperature of the low pressure turbine. State 7 increases the temperature of the low pressure turbine intake back up to the combustor outlet temperature. So T7 is equal to T5. We're adding just enough heat to boost the temperature back up. And we also have the same pressure ratio, RP is 3, and we have the same isentropic efficiency. So if you go through and you do the whole analysis all over again for the low pressure turbine, you're going to get the same exact specific work. So work for the HPT is equal to specific work for the LPT, which is 282 kilojoules per kilogram. WLPT, 282 kilojoules per kilogram. Okay, I'm just writing these up here just to keep track of stuff because I'm doing a lot of erasing. All right, just keep track of stuff. Okay, so you can see where these outputs and where these numbers are, what they're referring to. Okay, so we have the works, specific works, good. Let's find the network. Let's find the network. What's the network for this thing? Specific work. What's W net? Well, W dot net, the actual power produced by this Brayton cycle, multi-stage or otherwise, is the sum of the turbine power, the sum of the turbine power minus the sum of the compressor powers. Remember, the turbines are driving the compressors, and any work left over is what you get from the device. Now I have 2 turbines and 2 compressors. So I have W dot HPC plus W dot LPC. I'm sorry, turbine, not compressor. Turbine, turbine, minus W dot HPC plus W dot LPC, okay? Now I can divide top and bottom by m dot for the air flowing through the cycle. So note, m dot equal m dot air is constant throughout the cycle. We're going to assume that the mass flow rates are all the same through the cycle. Again, I just mentioned last time, in reality, in the combustor, you're adding fuel. You're adding a small mass flow rate of fuel that is then getting burned. In the reheater, you're adding a small amount of fuel. It's getting burned, and it's increasing the temperature back up. So in reality, in a real Brayton cycle, you're actually going to have different mass flows through each part of the device. M dot air through the LPC and the HPC are going to be constant, but as soon as we get to the combustor outlet, M dot is going to be a little bit higher because you've added the fuel flow in the combustor, and then it's going to be higher still when you add the fuel flow in the reheater. We're not interested in that. We're assuming M dot is the same, and in almost all of these problems, M dot is the same for each device. Okay, so I can take the m dots, w dots, and I can rewrite that as specific work. So the net specific work is W net of the HPT plus W of the LPT minus W of the high pressure compressor minus W of the low pressure compressor. We already have some numbers here. Let's see, the LPT and the HPT both produce 280 kilojoules per kilogram. And both of the compressors consume 139 because they have the same efficiency, the same inlet conditions, and the same pressure ratios. So let's crank that out. Let's crank that out. Let's see here. 286 kilojoules per kilogram. 286 kilojoules per kilogram. Okay, so W net, the residual work per unit mass flow, W net is equal to 286 kilojoules per kilogram. Another answer. Whew, I'm getting tired. There you go. Okay? In fact, I'm going to break right here. Okay, so let's calculate the total heat addition per unit mass, Qn. Not Q dot, Qn for this device, Brayton cycle. And of course, after that, we can immediately calculate the efficiency because we know the net specific work. So what's Qn? Well, first of all, Q dot in, rate of heat addition in to our Brayton cycle here is composed of 2 sources. The heat added to the combustor and the heat added to the reheater. Heat is being added to the system in 2 locations in our device. So we have Q dot combustor, and then we have Q dot reheat, both of which are used to increase the temperature of the working fluid, okay? Now, of course, we're assuming the mass flow rates are the same through all devices. We're assuming m dot for the fuel is small compared to m dot for the air, fine. And if you divide through by m dot, you get Q in is equal to Q combustor plus Q reheat. So we need to find these heat additions separately. So if we apply an E-balance for process, let's see here, the heat addition process in the combustor, that is process 4 to 5. That's where the heat addition occurs in the combustor. 4 to 5. So process 4 to 5, which is isobaric heat addition in the combustor. Neglecting changes in kinetic and potential energy, steady state, no work. I get Q combustor is equal to the outlet enthalpy, H5, minus the inlet enthalpy, H4. Now, H5 I already have. It's 1278 kilojoules per kilogram. H4, what is H4? Let's look at state 4 here for a moment. So H4 is the high pressure compressor outlet state. So here's H4 right here. So if I apply the energy balance for the high pressure compressor, if I apply the energy balance to the high pressure compressor, I will get that H4 is equal to H3 plus the specific work for the compressor. So note. We look at process 3 to 4. We have W, high pressure compressor, is equal to H4 minus H3. And this is from the energy balance. No change in kinetic potential energy, steady state, no heat interaction. Okay? Now, I know WHPC, and at one point I already wrote down H3. It's actually equal to H1. Remember? H1 is equal to H3 because T1 is equal to T3. So let me, H3 is equal to H1, well, is equal to H evaluated at T3, which by the way is equal to T1, which is 300 degrees Kelvin. So H3 is equal to H evaluated at T3, which is equal to T1. Remember, that's given in our problem statement. Okay, so what is it? 300 kilojoules per kilogram. So 300 kilojoules per kilogram. So I get, okay, so H4, sorry about that. So H4 is equal to H3 plus WHPC. Let's see here, H3 is 300 kilojoules per kilogram, and the specific work for my high pressure compressor, 139 kilojoules per kilogram. 139 kilojoules per kilogram plus 139 kilojoules per kilogram. So H4 is equal to 439 kilojoules per kilogram. Okay? So I have H5 and now I have H4. Thank God. Let's see here. 1278 minus 439, and that's kilojoules per kilogram. And that's going to be equal to, oh boy, I think I need my calculator for that one. 1278 minus 439, I get 839 kilojoules per kilogram. So I'm going to put that down in my diagram here. 839. So Q combustor equals 839 kilojoule per kilogram. Okay, good, I got that. All right. Listen, I hope this is driving home the point that you need to get comfortable drawing the TS diagram for the cycle or the process or the device, drawing the device, indicating the various states. If you don't do this, you're screwed, okay? So for those of you that are doing your problems without doing your TS diagrams or PV diagrams or some kind of a diagram, and you're not drawing the device, you are utterly lost and you're screwed at this point, okay? So start drawing your TS diagrams. All this cycle stuff is only going to get worse. This is pretty serious. This is pretty serious. It's actually going to get, it may get a little more serious, okay? This is about as bad as it gets, maybe a little more, maybe, but you can't do this problem without a cycle diagram. Okay, so I have Q combustor now. Boom, done. Now I need to get the Q for the reheater. Oh boy. Q for the reheater. Well, the reheating occurs from state what? State 6 to 7. So process 6 to 7 is the heating and the reheater. So process 6 to 7. So this is heat addition in reheater. I applied energy balance to the reheater. Steady state. No change in kinetic and potential energy. No work. And I get H7 minus H6, the specific heat added kilojoule per kilogram of flow to the reheater. Okay, now, a couple of things here. H7, let's look at state 7 here very quickly. Let's look at state 7. We are told that the temperature at state 7 is equal to the temperature at state 5. The reheater adds just enough heat to get you back to the original combustor exit temperature. That means that H7 is equal to H5 because the temperatures are the same. So H7 is equal to H5. So this is actually equal to H5. Check, I've got that. There it is right there, okay? There it is right there. H6, oh boy. Well, let's look at the process 5 to 6. Let's look at process 5 to 6, which is the expansion in the high pressure turbine. 5 to 6, the expansion in the high pressure turbine. If I apply the energy balance to the high pressure turbine, no change in kinetic energy, steady state, no heat interaction. So for process 5 to 6, so this is expansion in high pressure turbine. I get WHPT is equal to H5 minus H6. Okay, so I need to get H6. So I'm going to look at the process 5 to 6. Now I have WHPT. I've already calculated that. I also have H5, so I can immediately get H6. So H6 equals H5 minus WHPT. Let's see, H5 is 1278, and the specific work for the high pressure turbine, we already calculated that, is 282 kilojoules per kilogram, 282 kilojoules per kilogram. Oh boy, 1278 minus 282. 1278 minus 282. 1278 minus 282. 996. 996 kilojoules per kilogram. That's H6. Oh boy. Okay. So H5 is 1278 minus 996 kilojoule per kilogram. Kilojoules per kilogram. You might guess this is going to be the WHPT. That's exactly what the work's going to be. So what the heat addition is going to be. So 1278 minus 996. So I get 282 back. 282 kilojoules per kilogram. So we went right back up to the original temperature. So Q reheat is 282, which is actually the work required output for the high pressure turbine. So Q reheat, or if you like, Q reheat, I know this is getting really small, 282 kilojoules per kilogram. Same as the work produced by the high pressure turbine. That's not true in general. If the temperature, if T5 and T7 were not the same, then Q reheat would not be equal to WHPT, okay? It's good to calculate this stuff from scratch. Okay, I have the heat addition from both the reheater and the combustor. I am ready to plug in. Let's see here. So I got Q combustor is 839 plus 282 kilojoules per kilogram. And I get the total heat addition. The total heat addition from the combustor to the combustor and the reheater of 1121. 1121 kilojoules per kilogram. 1121, that is the total heat input or added to the Brayton cycle here per unit mass flow. So I'm going to write Q in, starting to run out of space, 1121 kilojoules per kilogram. Okay? Now I need to calculate the efficiency. That's easy. That's a one-liner. Thank God. Something's a one-liner. Oh, this problem. Some of these problems, they get so long. They get so long. Okay, efficiency for my Brayton cycle. So efficiency, eta, is equal to the net power produced divided by the total heat input per unit time. Of course, we can divide by m dot. And I get W net over lowercase q in. I have both of these quantities. The net power, net work per unit mass, 286. 286 kilojoules per kilogram. And the total heat input was 1121. Kilojoules per kilogram cancel out. I get 281 divided by 1121. 281 divided by 1121. 281 divided by 1121. And I get 25%. 25%. Okay? So the efficiency of this thing is 25%. That's without any regeneration going on. We're going to talk about that in a minute. So eta equals 25%. Ooh, running out of space. There we go. Running out of space. 25%. Not too hot. Only a quarter of the energy consumed by this Brayton cycle. Only a quarter of it, released by burning the fuel, is turned into usable shaft work of some kind. Okay, shaft work. Okay, let's see if we can increase this. Let's see if we can increase this here. Let's say, and this is going to get very crowded. How am I going to do this? Let me take the LPT here. We know all these numbers. Let me take the LPT, and I'm going to take, oh boy, I'm going to take, what's a good way to do this? Remember, our regenerator efficiency is 75%. I think I'm going to move this stuff all over. So I'm going to take this all, oh man, not a lot of room. I guess I'll leave it up here. Okay. Here's my regenerator, my heat exchanger, which is a regenerator. And I'm going to take, and I don't need any of this anymore. I know what these are. So I'm going to send it into the regenerator. Out. Okay, so I have a regenerator. So there's a certain amount of heat here. Q dot regen. I know you can't read that, but that says Q dot underscore regen. So some heat is being transferred from the hot. Oh, I erased too much. From the hot low pressure turbine. Don't want to get rid of my LPT. So from the hot low pressure turbine, so some of that waste heat is taken from the hot LPT exit and recycled back into the cycle. So instead of changing all my notation here, I'm going to keep this as state 8. I'm going to keep that as state 8. I'm going to keep this. This is still 4. This is still 4 right here. No. I'm going to call this 4. The HPC outlet, I'm going to call 4. And I'm going to call this state right here the combustor inlet. I'm not going to give it a number at all. I'm going to give it a symbol, X. So I'm going to make this an X. So the idea here is that we're taking waste heat. We're taking waste heat, Q regen. We're taking waste heat from the low pressure compressor exit flow, and we're dumping it into the high pressure compressor exit to preheat the flow before it gets to the combustor. Now, the effectiveness here. Let's write down the equation for the effectiveness. Let's apply the regenerator effectiveness to this problem. So effectiveness regen, and that's 75% by the way, is equal to Q dot regen over Q dot max. Now the maximum, so if I divide this by m dot, I get Q regen, lowercase q, divided by Q max. Now the maximum heat transfer is the difference in temperature between state 4 and state 8. The high pressure compressor exit and the low pressure turbine exit. So the maximum is H8 minus H4. That's my Q max. H8 minus H4. That's the maximum possible heat transfer. Okay? So let me calculate Q regen. Let's calculate the heat transfer per unit mass in my regenerator. So here's my regenerator. Regen. There we go. Okay. Q regenerator equals the effectiveness of the regenerator times H8 minus H4. H8 minus H4. The effectiveness is 75%. Check, I got this. H4, I think I had that at some point. I must have had it because I calculated the combustor inlet. So I can go find this again. H8, that is the low pressure turbine exit enthalpy. Okay, we need to calculate some of these things. Let me see if I can find H4 here. H4, I have it here somewhere. Yeah, 439. 439. So H4 is 439. I'll put it over there. H4 is 439. H4 is 439 kilojoules per kilogram. I must have had that at some point. Okay, so I need to find H8. I need to find H8. Well, if I apply the energy balance to the low pressure turbine, then WLPT is equal to H7 minus H8. Okay? So WLPT is equal to H7 minus H8. So process 7 to 8, that's expansion in LPT, and I get WLPT, which I know is equal to H7 minus H8. H7 minus H8. I'm running out of chalk here. H8 is equal to WLPT plus, minus WLPT plus H7. I have WLPT, it's equal to 282. So this is equal to minus 282 plus H7, which is actually equal to H5. H5 I already had written down. That's the H5. I have it here somewhere. 1278. 1278 kilojoules per kilogram. So H8, let me crank that out. See, 1278 minus 282, 996. Where have I seen that before? 996 kilojoules per kilogram, 996. So that's H8. Check. Okay, let's calculate the heat transfer inside the regenerator. 0.75 at 75%, 996 minus H4, 439 kilojoules per kilogram. And I get the heat transfer minus 439 times 0.75, and I get 417 kilojoules per kilogram. So Q regen is equal to 417 kilojoules per kilogram. Okay? So we're, oops, sorry about that. Just plugged in for H8, H4, and the regenerator effectiveness. 417 kilojoules per kilogram is the heat transfer from the hot LPT exit gas into the cool HPC exit to preheat the air. Okay? Now, what's the total heat transfer for this system once I have the regenerator? Well, instead of having to add the full 839, instead of adding the full 839 kilojoules in the combustor, I only have to add 839 minus 417. Minus 417. Okay, so let me write the revised expression here. So Q combustor plus Q reheat. So that's going to be equal to, oh boy, did I erase it? So that's going to be 1277, sorry about this, minus 439. That's going to be 838. 838 minus what I added with the regenerator, 417, plus what I added in the reheater. And what was added in the reheater was 282 kilojoules per kilogram. Okay. So this is Q regen. I don't have to add that heat in the regenerator. In the combustor, I added it in the regenerator. So we have 838 minus 417 plus 282. And our new heat addition drops down to 703 kilojoules per kilogram. Before, without the regenerator, it was 1100. Without the regenerator, it was 1100. It's dropped down to 703 kilojoules per kilogram. Let's recalculate the efficiency with the regenerator. Let's calculate the efficiency with the regenerator. So eta, and that's with regeneration. So that's going to be the work, the net work, 282. So work net divided by Qn. And this Qn is now with regen, and this is now with regen, and I get W net 286 kilojoules per kilogram divided by 703 kilojoules per kilogram. They cancel out. What's my new efficiency? What's my new efficiency? %. It's actually 41%. So the new efficiency with the regenerator is 41%. Without the regenerator, it was 25%. No regenerator, it was 25%. So we bumped up the efficiency almost by a factor of 2. Almost by a factor of 2. How close is this efficiency to that of a Carnot cycle operating between these two temperature limits? So let's say we have a Carnot cycle. Let's finish this off by calculating the efficiency of the equivalent Carnot cycle operating between Carnot cycle, W dot cycle, Q dot in, Q dot out. Let's see here. Let's figure out what our maximum or our high temperature is and our min temperature are. Let's figure out what these are for our cycle. Let's see here. The minimum temperature in the cycle is T1 and T3, which were 300 degrees Kelvin. And the maximum temperatures I had written up there were 1200 degrees. So I have 300 and I have 1200. 1200 and 300. So the efficiency, Carnot, which is actually my maximum efficiency, is 1 minus T min over T max, or 1 minus 300 over 1200. Oh boy. Well, let's see what that is. 1 minus 300 divided by 1200. 75%. So the Carnot cycle, note, eta max, or eta Carnot, is 75%, operating between the same two temperature limits. Well, with regeneration, we're awfully close. Well, we get closer with regeneration, 41% versus 75. Without regeneration, recycling some of the waste heat, 25%. That's pretty lousy, okay? All right, ladies and gentlemen, that completes our lecture. Take care.